So good afternoon. So this session is about Aicte Prerana scheme for preparation of the GATE and other higher studies for SSC students. So this is conducted from Erode Sengunthar Engineering College, and myself, J. Arun Prasad, Assistant Professor in Department of Civil Engineering. So today I am going to handle the session regarding structural engineering. So from the GATE syllabus, we will be dealing with structural engineering. From that section, we will be dealing with structural analysis. Okay. So previous class we have discussed MCQs up to 23, right? So today we will be continuing the MCQ. 24th question will be flexibility matrix is a square symmetrical matrix. Stiffness matrix is a square symmetrical matrix. Both A and B are none of the above. So which is the correct statement here? So the answer will be C. So flexibility will be, that matrix will be a square matrix also, and stiffness matrix also will be a square matrix. Okay. So next question. Degree of static indeterminacy. So here we need to find the static indeterminacy for a rigid jointed plane frame. Okay, assume a rigid plane frame having a 15 members and 3 reaction components and 14 joint. So what will be the degree of static indeterminacy? So the options are 2, 3, 6 and 8. So if you are using the formulas and if you are finding that degree of static indeterminacy, the answer will be 8. Okay, because we have 15 members and 3 reaction components for support ends. Okay, and 14 joints we have. So next question. Flexibility coefficients depends upon loading of the primary structure. So in the flexibility matrix method, the flexibility coefficients depends upon the loading of the primary structure. So whether it is a true or false. Okay. Or depends upon the loads applied. The flexibility coefficient, whether it will be depending on the loads, whether it is true or false, or depending upon the load applied, or none of the above. So here the answer will be B. Okay. So it will not be depending upon the primary structure loadings. So it is a false. Next, how many compatibility equations would be written if we have n number of redundant reactions? So if you are having n numbers, infinite number of redundant reactions, what is the compatibility equations? How many equations it will be there? N minus 1, n plus 1, or n plus 2. So the answer will be n. Okay. So next one, the flexibility matrix is always symmetric, non-symmetric, anti-symmetric, or depend upon the loads applied. So the matrix which we are obtaining now, flexibility matrix method. So that matrix will be either it will be symmetric or non-symmetric or anti-symmetric, or depending upon the load it will be varying. So it will be symmetric matrix. Okay. So next. So the numerical accuracy of solution increases if the flexibility coefficients with larger values are located. So I'll repeat again, the numerical accuracy of the solution increases if the flexibility coefficient with larger values are located. So what will be the answer? Near main diagonals, near edges, in between, near side middles. Okay, so where the solution accuracy will be there. So it is near main diagonals. So which of the following, next one is, which of the following primer structure is best for computational purpose? Symmetric, non-symmetric, anti-symmetric, or depend upon the load supply. So the answer will be symmetric. So symmetric primer structure will be, you can use for calculation or analysis parts, it will be easier, and calculation part will be easiest. Okay, the next one, for computational purposes, the deflected primer structures or actual structure should be, for computational purposes, the deflected primer structure and actual structure should be different as possible, similar as possible, it doesn't matter, in between. So for computing, for analyzing, that deflected primer structure should be different from actual structure or similar, or it should not be considered, or in between. So what will be the answer? So it should be similar, whatever the actual structure we have, and the deflected primer structure should be same. So next, indeterminate analysis of a symmetrical structure is different. It is difficult from the tough non-symmetric one. So while you are analyzing the indeterminate analysis, no, symmetrical structure is difficult from non-symmetric analysis. Whether it is true or false. Okay. So the answer for this question will be false. So whether you are analyzing a symmetric structure or a non-symmetric structure in the determinate, that is in indeterminate analysis, it won't be difficult when comparing to the symmetric and non-symmetric. Okay. So next, in general, any structure can be classified as symmetry 1. When the structure is symmetric, when its loading is symmetric, when its supports are symmetric, when it develops symmetrical internal loading and deflections. So when we will be saying the structure can be symmetric 1, what are the conditions? In generally, so the structure should be symmetrical, or the loading should be symmetric, or the support should be symmetric, or when it develops a symmetric internal loading and reflections, and the internal forces will be symmetric. So what will be the answer for this? That is when the structure develops in the internal forces, that is deflections and loadings and stresses and everything. If it is symmetric, then the structure can be classified as a symmetric one. Normally, which of the following things may be or may not be symmetric to develop symmetricity? So to develop a symmetricity, what are things may be or may not be considered? Material property, or geometry, or loading, or DKI. Okay. So what we need to consider? So the answer will be DKI. Okay. So next one, We have a figure here. We'll be discussing so this structure is made redundant by temporarily removing how many support reaction? 1, 2, 3, or 4. So consider this diagram. That is, we have A is a fixed, C and B is a hinge. We have a point load acting at the point C. So the structure made redundant by temporarily removing how many support reaction? So the answer will be 1. That is A. Okay. So the structure, by removing the one support, we can make this total structure can be a redundant one. Next, indeterminate analysis of an anti-symmetrically loaded structure is difficult from that of a non-symmetrical one. Okay, is it true or false? So indeterminate analysis of an anti-symmetrical, that is non-symmetrically loaded structure, is difficult from a non-symmetrical one, or depends upon the load supplied, or none of the above. So the answer will be, it's not difficult one, so it will be similar to that of the anti-symmetrically loaded structure for analyzing the indeterminate analysis. Okay. So next, again we have a same diagram. So we have a beam of A is a fixed one, fixed support, and B is a hinge, and we have a point load at the point C. The above structure is statically indeterminate. State whether the above sentence is true or false. Whether this structure is a statically indeterminate. We need to check it. Use the indeterminate formulas. And if you are finding whether we can check it indeterminate, statically indeterminate. Yes, it is a statically indeterminate structure. So we have a fixed supports a 3 reaction and hinge we have a 2 reactions. And if we are using the formula for indeterminate, we will be getting a indeterminate structure, statically indeterminate. So next, according to Maxwell theorem, which one of the following is correct? FAB equal to FAA, FBB equal to FAA, FBA equal to FAB, FBA equal to FBB. So which condition is correct? So we will be having a FBA equal to FAB. Okay. So next question, that Maxwell theorem doesn't apply when external moments are placed on the beam. State whether the above statement is true or false. So whether we have to say the statement is true or false, that is, in Maxwell theorem, when we are applying an external moment, the Maxwell theorem won't be applying. That condition will be satisfying. Whether the statement is true or false, we need to find. So that is a true or false. So it doesn't have like this statement. So it can be applied when the external force is not applied also. So next, first step in this method, that is Maxwell method, to find the stiffness coefficient, state whether the above statement is true or false. So it is false. Okay. So next one, what is the SI unit of a stiffness coefficient? So in stiffness matrix method, we will be using the stiffness coefficient. Now, what is the unit of that? Meter per kilonewton, kilonewton per meter, kilonewton or meter. So the answer will be kilonewton per meter. So stiffness, no, load by displacement will be having it. So we'll be having kilonewton meter. So next, which of the following is unknown in stiffness method? So in stiffness matrix method, which is the unknowns we are using? Force, displacement, support reactions, or none of the above. So we know that displacements are the unknowns for the stiffness method. So answer will be B. So next, degree of kinematic indeterminacy is used in this method. State whether the above statement is true or false. Okay, so in degree of kinematic indeterminacy, use whether the statement is true or false. So it is a true statement. Okay, that is in stiffness method we are using the kinematic indeterminacy. So next question. How many rotations are possible in case of a three-dimensional frame or beam? Okay, whether you are going for slope deflection or if you are going for flexibility. So how many rotations are possible in case of a three-dimensional frame and a beam? 1, 2, 3, and 4. So the answer is 3 rotations are possible in case of a frame and beam. It is 3-dimensional frame and 3-dimensional beam. Okay, so 3 rotations can be possible. Okay, so next, which of the following are not usual places for the nodes location? So which of the following are not usual places? Joints, supports, point of change in the cross section, or inflection point of bending moment diagram. So read the question again. Which of the following are not usual places for the nodes locations? So we are placing the nodes, right, which is not exact location. So in joint, whether we have a node location, supports or point of change in the cross section or inflection point of a bending moment diagram. So we'll be having an inflection point of a bending moment diagram. So in joints we'll be having a nodes location, supports also we will be having, and in the change of the point, it is a cross section changes now. At that point also we will be having a nodes. Only in the inflection point of bending moment we don't have a nodes. Okay, representation we don't have nodes there. So next question. How many linear displacement can be done? Sorry, how many linear displacements can a node having 2-dimensional frame beam? So in a 2-dimensional frame, whether you're considering beam or frame that is 2-dimensional, there's a node. How many linear displacement the nodes can have? 1, 2, 3 and 4. Okay, so the answer will be 2. So how many linear displacements the node can have? So it will be having a 2 linear displacement in a 2-dimensional frame. So we are not asking about 3-dimensional. So we will be having a 2 linear displacement in 2-dimensional frames. So next, so which are the following methods for solving indeterminate structures are easiest for computational purposes? So below some methods are given. So which method is easier for solving the indeterminate structures? Force method, displacement method, method of consistent deformation, moment area method. So which are the following method is easier? So it will be displacement method. Okay. So next one, which of the following loads are not carried by a beam? So which loads will not be carried by a beam? Axial load, shear load, bending load, or flexural load? So which load is not carried by a beam? There's 4 options, that is axial, shear, bending and flexural load. So axial load, the answer is axial load. So the axial load will not be carried by a beam. So remember this, shear load it will be carrying, bending load will be there, and flexural load will be there. Only axial load will not be carried. So which of the following is carried by a truss members? Shear load, bending load, axial load and flexural load. So in a truss member, which load is carried? Shear load will be there, bending load, axial or flexural. So here the axial load will be acting. So in case of a beam, no, axial load will not be there. But in case of a truss members, the axial load will be there. Okay, so don't confuse the beam members and truss members. So next one, the internal degree of indeterminacy of a beam of frame member is always 0, always non-zero, depend upon the internal hinges, none of the above. So in a beam or member, the internal degree of indeterminacy will be 0 or non-zero or depend upon the internal hinges, and none of the above. So depend upon the internal hinges available, that is provided, will be having an internal degree of indeterminacy. So it will not be 0 or non-zero. So we can't say accurately whether 0 or non-zero. Okay. So if you are having a 2 hinges, the answer will be, the indeterminacy will be 2. If it's a 1 or if it's a 0, it will be varying depending upon the internal hinges provided. So next, how many extra equations are possible if 3 hinges are there in a plane, there is a plane frame in relation to DSI? So again I'll read it. How many extra equations? How many equations are possible extra other than the compatible equations and everything for a 3 hinges in a plane frames? How many extra equations are possible? 6, 9, 3 and 1. So what will be the answer? So consider a plane frame and make it it is having a 3 hinges. Try to find out the degree of static indeterminacy. So how many equations will be required? So if you're solving, you'll be getting, that is, if you're solving, you'll be having a need of 3 equations. Okay. So now another question. So how many extra equations are possible if 3 hinges are there in a space frame in relation to degree of static indeterminacy? So here in the previous question we had plane frame. So here we are having a space frame. So again the same thing, only the difference is space frame. So try to find this. So if you're finding what the answer will be, whether it is 6 or 9 or 3 or 1. So the answer will be 9 equations will be having, since it is a space frame. So that will be need of extra equations as 9. But in the case of this plane frames, no, we need only 3 extra equations. Since the frame is in space, so will be required 9. That is the difference of both. So next one, I hope this is the last one. If an internal hinge is there in a frame member, so in a frame member, if there is internal hinge, then this member is stable, unstable, or determinate, or none of the above. So again I'll repeat, in a frame member, if there is an internal hinges, then the member will be stable or unstable or determinate, or none of the above. So it will be an unstable member. It's an unstable one. Okay. So I think we have questions. Okay. So next, if all the segment of a truss forms a triangle, then the truss is. So we have a trusses. The truss, each segment forms a triangle. Then the truss is a internally stable or externally stable or internally unstable or externally unstable. So consider we have a trusses. So each segment, okay, of a truss forms a triangle. Let's say each members joined together, it will form a triangle. Then the truss will be internally stable, externally stable, or internally unstable, or externally unstable. So what will be the answer here? So it will be internally stable, because we have each segment forming a triangle. So it is stable internally. Okay. So I hope everyone clear with this MCQs. We have covered basics of this flexibility matrix and stiffness method. So in previous class we have discussed some basics of the structural engineering. Okay, and some MCQs regarding that slope deflection. We have discussed what is a determinate, what is structural analysis, and difference, and we have discussed some few basic MCQs regarding this structural analysis and result. We have discussed that few methods. First, slope distribution we discussed, moment distribution we have discussed, and energy method we have discussed. Okay, and today we are discussed in the flexibility and stiffness matrix method. So we are discussing only the MCQs in the basic part. We didn't go deeply about the analysis. So that analysis part and remaining will be discussing in the further classes in the future. Okay. Thank you.